Are we live? It's echoing. Yeah. Echo. Sorry, folks, we'll be starting in a minute.
Hello, better? Logesh?
Yeah, Manga, I can hear you now.
Okay. Thank you. I was just talking about what DevDay is. So DevDay is a monthly event powered and posted by Sahaj, where we come together as a developer community and share learnings and initiate tech conversations. Today, we have yet another exciting episode of DevDay, where the topic of the conversation is autonomy at scale and what's the future. To present that, we have an amazing speaker amongst us. It's for the fear of missing out any of his accomplishments, I have noted it down and I'm going to read it out. So, Dr. Arjun Jain, welcome. Dr. Arjun Jain is an adjunct faculty at the Center of Data Sciences at Indian Institute of Science. Dr. Arjun Jain is also co-founder and CEO of UAVIO Labs and also the chief data scientist and co-founder at fastcode.ai. UAVIO brings us the most advanced commercial drones performing autonomous missions. Fastcode.ai builds city solutions, computer vision solutions for driverless cars, sports analytics, inspection, and surveillance. Previously, he co-founded Perceptive Code Learnings, LLC, a Silicon Valley startup that builds intelligence into automobiles. Arjun has worked for several companies, including Yahoo in Bangalore, Weta Digital in New Zealand, and Apple. He has especially been active in the human sensing related industries. Arjun served as a developer for Weta Digital's motion capture system. This system has been used in many feature films, and Arjun was credited for his work in Steven Spielberg's The Adventure of Tintin, 2011 movie. Arjun's work has resulted in several academic publications with currently over 5,000 citations, patents, and has been featured by mainstream media, including in the magazines Discovery, BBC, Vogue, etc. And I have not even touched upon his academic qualifications. Before I usher in Dr. Arjun Jain, I would like to invite Dr. Ravindra Babu to do the honors. So, Dr. Ravindra Babu is the Chief Data Scientist at Sahaj. Would you like to add a couple of words?
It's an honor. It's an honor to have Dr. Jain with us. And as Malini said, his accomplishments are mind-boggling. At such an young age and kind of accomplishments he had is really inspiring to all of us what we can do in future. Thank you, sir, for accepting it.
Thank you so much for that very kind introduction, Malini, and for those kind words. So, without further ado, let's just get started. So, as you know, the topic for today is autonomy at scale. Where are we headed? And let's try and make it interactive. If you have a question, just maybe raise your hand and we'll take it from there. So I'll do some logical breaks. So, what we will discuss today is first some of our own work in automotive, then a very brief history of autonomous cars. We'll talk about two types of autonomous agents, ego only and end-to-end. We'll then talk about the future, where I think it's headed, and that's the hybrid approach. We'll then talk about what it takes to do this, so the data factory. We'll talk about sensors and redundancy, some stories, why simulation is essential, some things that do not get the limelight as much, which is the hardware and on-the-edge compute, and finally the million-dollar question: where will we actually get there, and maybe more so in India. So first, our own work. So we've worked both inside the car and also outside the car, so to speak. So this is a video from Paris, the Paris Auto Show, and this is Vocalization, our line manager, and he's essentially demoing the system. So what we've done is we've put a camera inside the car, just behind the rear view mirror, and based on that, we can realize some user interface kind of use cases. So what we do is we localize his hand, his joints of the fingers and arm within the cockpit, and when he takes his hands close to the touchpad, the touchscreen, you see that the corresponding icon is highlighted. Because it is the driver hand, we can distinguish between the driver and passenger. So whenever the driver takes his hand close to the system, the corresponding seat gets highlighted, so it's one click less. And not just the touchscreen, but because we can localize it within the entire cockpit of the car, the trackpad, if you also take it close to the touchpad, you will have the same behavior. And then there are some gesture-based use cases, some favorite pose. So the speed pose is a favorite pose. You can tie various functions to it. Here you see that it goes to ambient lighting and so on. So this was the start. So this is what Mercedes did with the company that we sold to them. And it took us 3 years to actually bring something from research to production. So when we started, we had this huge network with around, the whole network would take 6 GB of the GPU memory. But then it was a challenge to bring it down to a single FPGA, Xilinx 33 FPGA, which had like 110 DSP units. So bringing it down from those 6 gigabytes to 300 kilobytes of weights and about 1.1 million activations. So that is what we did for 3 years. And this was fun. So this is the Mercedes top line, it's the Maybach model of the Mercedes car. Here we also have cameras in the back. And here we achieve some implicit use cases, not explicit, but because we know the position of the head, it automatically gets exhausted. Explicit hand gesture, but I like more these implicit things that just happen automatically. This is again an implicit gesture. I mean, you would do this if you want to get to the seatbelt, and the seatbelt presents itself. So yeah, and the most important thing here is, Mercedes, the motto is best or nothing. So best or niche, and you cannot make mistakes. So like maybe 999 times out of 1,000, it should be correct. So that is the achievement here. Of course, doing it on hardware and making it so accurate that you achieve a few sigma kind of performance. We published a bunch of papers with them. They also gave us a grant at IIT Bombay. When I was at IIT Bombay, we published a bunch of patents. So that is what is proof that we actually did it. Other than that, of course, it's all IP belonging to them. So this is then our work for the autonomous use cases, right? So here we do person detection. And here you see this is joint work between Mercedes-Benz, Robert Bosch, one of my companies, and Indian Institute of Science, and Mercedes Germany as well. And so here are 2 people from my company and others from other companies. So again, here it's all about accuracy, of course. This is a safety critical application. And you also want to get to speed. So this is on the y-axis, you have the accuracy, lower is better, and on the x-axis is the time that it takes to forward prop that model. So mass parsing in a common model is somewhere around 80 milliseconds. You don't have so much time. So we achieve something which is around 19.3, 19.5 milliseconds. Now of course, most of you would know this, but the question is, why could we achieve, for example, the use case in universities only in 2018? We've been doing human codes forever. So one of my advisors, this is his paper from 1998, this is my paper from 2010. So to enable the previous application, we needed to estimate the 3D hand position within the car. And we've been doing it for a long time. However, it was never good enough for industry. And in 2012, AlexNet happened, after which, it changed the whole world. So a very quick history of autonomous cars. Nothing new, people have been doing this, say, since the late. So for the Prometheus project in Europe, the Beta 2 by Daimler-Benz could already drive significant distances on the highway. We then have the most popular DARPA challenge in 2004. Perhaps the most interesting information about this is that nobody succeeded this off-road track, and the main reason was that no human intervention was allowed. And so, nobody could really complete this event. But then a similar one happened next year in 2005, and this time 5 teams managed to complete this event. And the the interesting thing here was that Velodyne, a LiDAR maker now, was then a startup and was the supplier to all the winning teams. So a lot of things came up from this kind of challenges. And then DARPA also had their urban environments in 2007. Of course, it was not a full-blown urban environment because it was a static world assumption. There were no moving pedestrians, moving cars, and so on. And 6 teams could also complete this event without a problem. Now, do we have any questions? So then, what kind of autonomous agents can you have, or autonomous, say in this case, cars can you have? The most popular, of course, is the ego-only system, where the agent has complete information about the environment, about the world, and it takes decisions autonomously just by itself. And then there can also be connected systems, where you may have partial information about the world, and then you communicate with other agents within the system, and then somehow integrate all this information. But more interesting today for us is only these ego-only systems, because it's a critical application, and you would not want to depend, on other agents, and you want a system which gives you some guarantees in terms of performance.
Multi-agent systems will be collaborative, cooperative. This is how typically we have been thinking. Also, like even within custom classification, even there they can be collaborative. And the ego only is an integrated system which also does multi-sensor fusion and able to make the decision. Or don't you consider the sensor fusion as another activity, another agent, or sensing as another agent? Then
yeah, so correct. You're absolutely right. I mean, of course, there are multiple sensors and fusion and everything. Here I meant when it is a different car or a different robot, for example. So that is what I meant by ego only and connected system. But yeah, I mean, so connected systems, it's not that connected systems do not exist and they add a lot of value. So all these high cars from GM in the US, like the Cadillacs, for example. So in the US, sometimes there are these pileups on highways where cars keep hitting each other from, because there is a fog or something and they're driving at high speed. So GM cars can talk to other GM cars, other Cadillacs, but then they cannot talk to any other car. So these are problems essentially with these V8s and so on. Now, again, of course, there is connected and ego only. There is also end-to-end or modular. So what do I mean by the sound is not good, somebody saying? It is
Continue on that.
Sure.
Just check it. You can.
All right. So, yeah, so end-to-end systems, like the name suggests, so you can do autonomy using end-to-end systems, and end-to-end systems are simply where there is an end-to-end deep learning framework between, say, the sensor measurements, like the inputs from a camera and a sat nav, GPS location, and then the idea is to do this uncertainty propagation from sensing to action, and the output should just be driving commands, such as how much to steer the steering wheel, how much to press the gas, or the brake, and so on. So this is at one end of the spectrum in terms of algorithms to do autonomy, and the other is where you have modular systems. So modular systems have this stack. We'll talk about the stack. The stack consists of perception, so perceiving the word, scene representation and localization, prediction, planning, and decision making, and finally vehicle control. So we'll talk about each of them in the next slide in a little bit more detail. So perception, as you all know, this is the dictionary meaning of perception. It's the ability to see, hear, or become aware of something through the senses, right? So the normal limits of human perception. And perception is a very hard problem. So in this image, for example, you need to identify all these moving vehicles. You need to identify static objects such as this traffic cone. You need to identify road signs and their meaning. You need to identify overhead signs. You need to identify traffic lights and the state, red, green, or yellow. You need to identify lane markings, solid, broken, yellow, double yellow, road markings, halt, school ahead, curbs, because there are humans there, crosswalks, and so on. Then you may also need to infer some specific tags for the environment. Are we in a residential area? Are we in a tunnel? Are we approaching a toll booth? And so on. So this is a long tail problem. So perception has a lot of these corner cases. For example, suppose we want to look at the object type vehicles, right? So all these are vehicles, and then each of them may have like a corner case in terms of the current state that it is in. For example, this is a vehicle, all right, but it has met with an accident and it's an upside down. These are all moving vehicles. I mean, it looks very different. There's a train, there's a woman with a pram, and so on. You also need to understand the state of these vehicles, meaning are the blinkers on, is the brake light on, is the parking light on, is it in a state of collision, and so on. Now let's take, so there are different, moving vehicle type here. Let's take a single type, which is say cars, but then again, cars can be very complicated. For example, this is an image of a big car. You can hardly see the car here. Here is an image of a car towing something, so it looks very different, and so on. So this is again an upturned car. And so even a subtask like car detection is a very difficult problem. And note that this is a safety critical problem, right? So 97% is not good enough. And finally, we need to get to 99.9999% accuracy. So suppose we want to capture behavioral corner cases. Suppose we want to capture, people who are very aggressive, people who are driving, say, very fast and very conservative, who are maybe driving below the speed limit. But by definition, there is not much training data because these are corner cases, right? So you're able to, your model is essentially representing this region of the distribution, and then you have problems with the two tails on the two sides. For the autonomous aerial vehicle, so Skydio is one of the market leaders, and this is from the Skydio website. So they say Skydio does not avoid moving objects or cars. Skydio X2 obstacle avoidance is off at night, and so fly with extreme caution. It says around reflective surfaces, still water, mirrors, and small obstacles, thin branches, utility lines, ropes, chain link fencing, etc. So these are all corner cases. And I mean, we can discuss and argue here, but there are there may be certain use cases when you solve just this bit, but then a lot of these use cases get left out of the long tail problem. Now I'm going to give you an example of, say, traffic light recognition. So traffic sign recognition. And traffic sign perhaps is one of the simplest object classes out there. Any ideas why? Any idea? Anybody? Like, why do you think I'm claiming this? It's because
The number of traffic signs are more or less constant, like 70 or.
It's constant and is always made to be well lit.
not necessarily. Sorry. No, it's the property of the object itself. So what is special about a traffic sign as compared to, say, objects or people or so cars and so on?
Static is clearly defined.
Static is one, so that is why it's slightly
Less
easier.
number of configuration and colors of graphic.
Yeah, it is a planar object. It's a 2D object, right? Everything else is 3D. You can have different views, but here, because it's a 2D object, you can. So it's a 2D object, so you can do a lot of things in the 2D domain instead of going to the 3D domain. So traffic sign is one of the easiest problems to solve, but still it has this long tail issue, and there are so many corner cases. There are about 600 signs in the US. Some of them are so rare that a data set of million images may have just 5 of those signs. You again need very high accuracy if you want to do autonomous driving. In this case, what we did was for one of the major tier ones. So this is L2, level 2, and level 3. We'll talk about these SAE levels later. And here we just wanted to display whatever sign we're approaching on the dashboard, right? Now, these signs should work without an HD map, without a known map of the area. So data imbalance is a big problem. Some rare signs have very few examples. And again, it has to be a low latency, high accuracy system. And I want to show you the system design that we have to do to finally enable this kind of a use case. So yeah, there is an object detector. Now the object detector can also do the classification, but there are 600 classes to classify. So it cannot do that at high accuracy. So the object detector gives us an object. It gives us a time. Is it a main sign? Is it an additional sign? Because you also need to do parent association later on. And it gives you a shape. Is it circular, square, triangle, and so on. You crop, and then you do a classifier for the fine-grained sign classification. You also do OCR, because optical character recognition, because a lot of these signs are text only, especially in the US. Right, and then finally you do this parent association, because signs can also appear in configurations where there's a parent sign, subsigns, and so on. So the point that I'm trying to make here is something as simple as traffic sign is already so complicated. So you would not have thought maybe that, oh, you really need to do OCR, can we not do without it? Do you really need to, can you not just run an object detector and get all the 600 classes right here? So it just doesn't work. Yeah.
So each module itself takes a certain amount of latency, right? So when you put up all the things together, that will.
Yeah, that's a very good question. So what you usually do is you have a common backbone. So you call it a multitask network. And this common backbone then has multiple heads on top of it. And there are some very interesting talks by Andrej Karpathy from Tesla, where he explains the engineering and the versioning of such systems. So it gets complicated, but that's the way to do it. So you'll have a common backbone which will run in around 18 milliseconds, and each of these heads will be maybe 2 milliseconds each, and they can run in parallel. So now let's talk about scene representation and localization. So by now we have perceived our surroundings. We know where the traffic signs are, where the other vehicles are, where the lane markings are, and so on. And now what we want to do is we want to represent that and ourselves within it, right? So what we want to do is, so if we want to know exactly where we are. Of course, we have GPS, but it will have, say, an error of maybe a few meters. The more expensive, but the more exact way to do it is to first collect a 3D scan of a neighborhood or the entire city, and then position yourself. So you can have a soft start based on the GPS. And then you can get a millimeter accurate positioning of yourself when you compare the current point cloud that you get from this LiDAR sensor, for example, with the high definition 3D map of the neighborhood. So this is one way to do localization. And the other is, for example, what Tesla is trying to do. So here they are doing it using vision only sensors. They don't have a real HD map. So they're able to position yourself in the 3D space with certain uncertainty, but then they're able to do all other tasks with this uncertainty. So it seems to work for them till now. So by the way, Tesla decided to also give up on their radar last October because of certain reasons, and now maybe they'll start using radar again. So currently Tesla is vision only. So this is the scene representation. So what you do is you then represent yourself, you know where you are in the scene, and then you also represent all the other objects. So all these are cars. So this is the pedestrian here. This is so yield sign they have found somewhere, and so on. So there are cars here. There is the intersection, and so on.
But the HD map, you mean the satellite image of the picture?
So what I mean is the 3D map. So like a LiDAR scan of the entire neighborhood. What Waymo is doing in San Francisco, for example.
Which the vehicle is taking? Or
No, what you have taken, no, by running these vehicles, but in a previous step. So what you've done is you have taken them, you've cleaned it up, you've removed dynamic objects from it, and now you have a very high resolution map, a 3D map of the entire neighborhood.
But what if the scenario somewhere changes? So maybe a new building comes up. Like, do they continuously update them?
Yeah, so they do at certain intervals, and if a new building comes up, you will still have a lot of support from things around it. You run an iterative closest point kind of an algorithm. So even if you don't fit in that area where, so you will still be able to fit, and you have tracking, you know where you came from. Assuming you do not have too many new buildings, this approach will still work easily. Right? So that was representing yourself and others in the scene. Now there is prediction, right? So prediction essentially means you want to predict where others will be. Any ideas why we need to do this? Why is this essential?
Collision.
Yeah, but then why can we not do it without the forecaster?
Is it because we need to decrease the latency of how much time does it take for the decision?
Yeah, I don't see your name, but yeah, exactly. Because we do not have enough time, because especially if you're on the highway, you have to realize that things are predictable. If you're doing something unpredictable on the highway, probably that's not going to end well, right? So people going straight will continue to go straight on the highway. And because you do not have enough time, suppose you want to overtake a vehicle, you need to predict where they will be, because if you take just their current measurements, you don't have enough time, enough milliseconds to be able to complete the task. Because you are on the road and you have very high, if you want to deal with this high speed objects with predictable behavior, you need to do this forecasting. So for example, here is a didactic case where you see they're trying to predict if the bicyclist would turn right, go straight, or stop at the traffic light. So they see that okay, they have a high probability. So this is just a didactic example to kind of explain. So you would usually not do it so much for the bicycle person and not so much in urban settings, but on the highway, of course, this is very good. So now once you've done the forecasting where you know the other agent will be, then based on that, you can plan your path, right? So in this case, you see this car and it knows that there's an object here, there's a moving vehicle here, and this vehicle will be here by the time this one will be here. So based on that, it has a certain selection of paths. They all carry a cost based on the end goal, and you can define what the cost is, and based on that, it takes the decision. Right? So, and another interesting thing is usually after perception, there is not too much of, say, machine learning. So these are essentially search algorithms like A* and so on. And finally, vehicle control. So even if you have the path that you want to follow, control is a big issue because there are errors in control. So what you want to do is you want to execute the path given by motion planning by giving relevant actuator commands to the steering, acceleration, etc. However, there are errors, generated due to inaccuracies in the vehicle model because of wheel slip, due to friction, because we're not modeling the physics 100% correctly. That's not feasible. So you need to also cater for inaccuracies in the system here. So
The brainstorm is how they use normal maps, Google Maps, and the existing data that it can be often.
So now what you have is you have, say, a bird eye view of the world, and you need to find a 2D path, where you have a function of time over, say, vehicle positions or positions. And then based on that, you need to come up with certain paths.
This is not online data. This is already existing data they use after the.
No, it's all online on the vehicle, right? Because now the vehicle is at every time step in the control loop, in the update function, you have this.
Among the number of paths it estimates, the A-star is operating on that.
Yes. So A-star is used to also get those paths, and then you choose one from them based on the cost. Each path can have a cost based on certain parameters, right? If it's taking you to if it's hitting other objects and so on.
So, I don't know.
Yeah.
So does it also predict what speed it should be moving, so as to be safe?
Yeah. So control takes care of that, right? Speed, acceleration, and brake. So
I mean, that's what needs to go to the vehicle. Yeah, so there are very hard time bounds here. So you use some kind of a robot operating system, right? So that it's all totally real time. Yeah, so I mean, if you, there's, I can mute it, yeah. Check, yeah. Yeah, so it's very time critical, and you need to make sure that you have set, say, time budgets for each module in your stack. Yeah, so that was the modular way of doing things. And we very briefly spoke about end-to-end way of doing things, and both have their pros and cons. So why do people prefer modular? So all these big companies usually have a modular stack as of now, because the modular approach helps divide tasks within a team. Engineering is easier. It's more interpretable. You can test each module at the interface, right? So these are clear advantages. Also, you can add hand-coded rules known as priors easier into each of these modules, because tapping into the output, you can make sure that it lies in a distribution, you pipe it into the next module and so on. And the drawbacks are that each step is performed in sequential modular silos. This does not really talk to this one, right? So they're all independent. And the stack has to be manually tuned for each change. And there is limited information shared across modules. And you don't train for the end task, right? So the end task is something here, but then here you're training for boxes and whatnot. Here you're coming up with the representation. I mean, the end task is something, but you're actually training, and the errors will all be propagated. If there are any errors here, there is no way for this guy to fix it, right? So errors will all be propagated. Yeah. Now, sorry. Yeah. Now let's talk about the other extreme, where you just give, your images, your GPS data into a giant network, a giant black box, for example, and out comes these vehicle control commands. So it's a simple design. It's a single AI system, and it's trained for the end tasks. But the downsides of doing this completely end to end is it's difficult to add these priors and rules, which I talked about. It lacks interpretability completely. So validation and safety are a problem. And it requires a lot of examples because because it's a very rich network, um, it has a lot of parameters, and you're training for the end task. So this is one of my, so this is Wave, one of my favorite startups based out of Cambridge currently. And they could, very quickly make this end-to-end system learn by driving it around for maybe a few minutes. So with maybe 20 to 30 engagements, engagement is when the driver takes over the steering or the car control, they could train this car to go around a certain neighborhood in the suburbs of London. Yeah, we'll talk about it. So they start usually with this bootstrapping of a model where, so we'll talk about it. So synthetic is the way to go, and it's really progressed a lot, and we'll talk about it in the next slide. And my favorite is, my bet currently is on this hybrid model. So where you do joint perception and prediction. So what you do is you predict some things, occupancy grids or occupancy maps, where, the perception is where you know where other objects are currently, and prediction is where you predict where they will be. And so the output would just be an occupancy grid, a 3D map with voxels where the others will be, and rest of it will be blank, right? And then you can have your other modules on top of it. So the advantage of a hybrid model is, somewhere in between. So you can maybe add a few rules. So one good example of this hybrid approach is work by Professor Raquel Ultrason. She started Wabi. I'll talk about it in a bit. And what she's doing here is, in comes, say, the voxelized LiDAR measurements, also some raster map and route that this agent should follow. And they then do this jointly. So, semantic occupancy forecasting, and then the motion planning separate. And this then becomes, safe, interpretable, and training somewhat end-to-end, not completely. So this part is trained end-to-end, and then this part is estimated on top of this one. Right, so this is basically the kind of algorithms people are trying for solving this very complicated use case, say the moon landing of our times in some sense. Now, another problem, or let's say another issue with doing things at this kind of a scale and with modern deep learning techniques is, earlier, if it was like, suppose you were doing vision pre-deep learning, everybody had access to this one computer, everybody had access to these simple tools, and there was, everybody could do something with those tools very quickly. But today, if you want to build these high quality models, you first need to build so-called this data factory. And then once you build this factory, you can then pipe a lot of models through it. So what does this data factory or this data engine usually look like? Well, you start with a bootstrapping database, a small data set of images. You train an initial model. You deploy it onto the target. So you assume you have some kind of a deploying mechanism, usually over the air. And then once it is on the agent, it tries to figure the inaccuracies. Now, note that you don't know the ground truth anymore, right? So if the car is driving, you don't know if your model is doing right or wrong. So, but there are ways to get this right or wrong. One, for example, using driver engagement. So if the driver is having to take over, meaning it's some kind of a corner case, if sensors are disagreeing, if tracking is failing, so those are, so there are maybe 200 such cases where you can collect data. So you identify these inaccuracies, you boost. So here, maybe it doesn't work for, say, tunnel kind of use cases. You collect such data, again, with a human in the loop. So it's not completely automatic. Maybe you want a recall of, say, 20%, where you get a bunch of data in, you then get it annotated by humans in the loop, and you then enrich your data set, you boost these images, and then you keep doing this, right? And at some point, your algorithm here will be good enough where it can just wake up, right? So the main strategy these days is to retrofit sensors on the car already or on your agent already, and then you let it learn. You don't charge for the sensors initially, and then you can charge for the final product that you would that you would have once you do this a bunch of times. Sensors are very important. So let's maybe not talk about them in too much detail. So of course, the main ones, be it a drone, be it a ground vehicle, are vision, camera-based, radar, LiDAR, location, and ultrasonic. These are some companies doing these sensors. And this is interesting and very important. So sensors should be complementary and redundant, right? Different cameras and different sensors have different strengths and weaknesses. LiDAR is sparse, but it gives you 3D information. Vision is dense, but it doesn't give you this 3D information. We all remember what happened with the Boeing 737 MAX fiasco. They did not have proper redundancy, and more important, they did not have proper software. So that's something that is really unacceptable. This is a small, so this is a 2020. So this is, summary of their review and the kind of changes that they have implemented. So what happened was that though they had, anybody seen this documentary by Boeing? Yeah. Yeah, exactly. So they had 2 angle of attack sensors, which should have been good enough. But the problem was their software was so bad that they were using data from just one sensor. Whichever was coming in, they were just controlling this MCAS system using any of the sensor readings, right? So if one is telling go down, then the other is saying no, don't go down. And then it keeps doing that. And finally, it met with these big disasters. And if you read this in detail, I'll not read the whole thing, but the only thing that it was, they eliminated the reliance on a single sensor. So it's not a hardware update. It's just a software update. And all they had to do was they will compare both these from both these sensors. And if, they will just disable this automatic STS, and they would provide the corresponding indication of such a deactivation on the flight deck. So that was actually had to be done to fix this issue. So even though they had these 2 sensors, they were not using them right in a redundant, fault tolerant way. Here is a quick comparison of sensor stacks within certain cars. So Google Koala has very nice mid-range LiDAR sensors, Google's own in-house sensors. You have the Tesla with 1 radar. Now this is gone. You have the X, Uber X, so Uber doesn't exist. They were bought over. And what we inferred was, Tesla works for reliable environments and standard driving use cases. Most corner cases are not manageable or with severe restrictions. Google has very good near field due to availability of LiDAR. And Uber XC90 had problems with missing LiDAR. So they had problems entering priority lanes and so on. Here's a similar comparison in the aerial vehicle domain. So you see that different models have different sensors. We have our own one, which we've not mentioned here, but yeah, like everybody has a different sensor stack, and depends what you can do with that. You need simulations. We wanted to, so we don't have too much time, so I'll rush over a little bit. But yeah, simulation I think is very important. In fact, simulation, so Google does a lot of simulation, and simulation is so good that you can do model training in the loop. So here is again some papers by Raquel's group, and you see that you're estimating this using a CAD model and then rendering a car here, and you can actually learn your model with the simulated data automatically without any annotations as such, at least the bootstrapped model. You also need a test facility, be it for ground robots or aerial vehicles, right? You just cannot fly everywhere. You need an airfield, or you need a system such as this one. So this is 91 acres in California. And again, compute is super important. So we talked about the multitask network and running the backbone within, say, 18 to 20 milliseconds, so that you can have this 33 or 30 millisecond kind of a turnaround time. And yeah, so these numbers, therefore, operations, because when you deploy your neural network model onto the edge, you can easily do that in 8 bits without losing any accuracy. So most of them you would read tops and not flops, because they're tera operations and not floating point operations anymore. And these are like huge numbers actually. So 144 tera ops, teraflops. So Titan V, which is an older graphics card, used to do 4 teraflops, right? So these are like, here it's, yeah, it's a lot of compute that you need on the car. So much so that Tesla is manufacturing their own thing and so on. These are some of the companies doing autonomous driving. These last 4 are, what I'm betting on. So I think they have been doing very well. I've been very lucky to work with a bunch of them. We're working with Volkswagen and Bosch and Mercedes. I was with the Apple's autonomous driving division back in 2015. And then we can hardly read this, but there are levels of automation for cars. Level 1, level 0 is no automation. Level 1 is driver assistance. Level 2 is partial automation. Level 3 is conditional automation, where you could give up control. Level 4 is when you can drive completely autonomously, where you can, in a geofenced region, where, so you remove steering wheels in the car, and as long as the car is within this region, it can be completely autonomous. So I believe that it will always be level 4. We will hardly get to like level 5, and we will have increasing levels of level 4. So the geofencing will keep on increasing. And then there's a similar one with drones. And level 4 is essentially high automation, where the pilot is completely out of the loop. And this is, I think, where we want to get to. Level 5 is where drones can maybe even do autonomous. It can decide what to do by its own and so on. So, and this is not like by any agency. This is by SAE. Here, there are just people trying to come up with a similar level of automation for aerial vehicles. And this is, I think, my second last slide. So, like people will always, I mean, I have this question, like, when will we reach true autonomy? So on the y-axis is the number of miles, and this is the human level. So humans usually do 10 to the power 8 miles, so 100 million miles before they meet with an accident. And this is until, say, 2020, cars were doing about, say, 10 to the power 4 miles without engagement. And this is what Professor Edwin Olson calls the Moore's law for autonomous vehicles, where this is doubling every year. And if you simply just extrapolate, you will get to like 2037. But 2037 is, in my opinion, level 5, where you have cars which can go almost everywhere. Let's see where we can at least have, reliable cars in, say, some developed cities in the world. And yeah, this is some footage from Hiranandani. And I'm just trying to make a case for India. And, so an autonomous car in India would need to know that there is a police officer here, or a security guard at least, who's trying to work with the traffic. There are people crossing the road. But the case to be made for India is that maybe you don't need to do a lot of things that you need to do in the developed world, right? Maybe you don't need to know about the traffic signs and the traffic lights and the lanes, and and cars are slow, so maybe it's easier to do it in India. And yeah, so this is my last slide, and we'll open up for questions. So this is, I'll just leave you with this. This is, sorry, yeah. So this is Tesla's full autopilot, or both in the urban setting and in the highway. I'm sure most of you have seen this video, but yeah, I'll just let it be as, yeah, like positive thing to end with. Sorry, how are the? So images are processed using the kind of hardware that I was showing you, using these edge devices in the car. And that's where, so images and other sensor data, images, radar, LiDAR is all processed on the car. Yeah, so I mean, it depends. I mean, are you talking about the driver or are you talking about people outside the car, for example, policemen or construction workers and school guards? So the first thing is just to stop, right? I mean, if you're able to do reliable people detection, I think you're solving 80% of the cases, and then you may need to do something specific for these special vulnerable roadside users. Yeah. I think it has to be, I mean, the responsibility has to be taken by the company. And no, so if the world truly is autonomous, then you would not need to own a car. There'll be robo taxis on demand and they will just pick you up and drop you wherever you want. But it has to be the company. I mean, who else can you really put the blame on? But none of them faced any criminal charges. Nobody went to jail. And so, yeah. So I'm talking about after pruning. So this is quantization. So you prune as much as you can using all the state of the art techniques. You start with already a very lightweight backbone. And then you can also do this quantization, and there are methods where you do not lose any accuracy. So losing accuracy is not an option, right? Even if you need to use more compute, but you can do int 8 without losing any. So unsigned. Yes, absolutely. Yeah. So mask arsenal, I mean, you would see that the accuracy was higher than this kind of. So, I mean, let me first answer, like what we did with Mercedes inside the car. So there we had an academic model at NYU, which was generic. So it was for people in the wild. But the car, the use case was constrained. It was inside the car. So the background was not changing. So for this kind of a case, you inherently can do it with a smaller, lesser capacity model. And then when we were doing this academic work, we were not really caring about the model size, the forward prop time, because we wanted to just win these competitions, right? Because nobody was really asking you for the time it took you to process that data set. All they were asking you was to, so then we did all this pruning, quantization, various techniques to come up to the most optimal model that you could deploy, which was still doing. No, so training does matter because now you have a much easier data set because it's inside the car. It's a fixed camera. So the background will always be the same. When we were doing it at the university, we are solving it for the most generic case without any priors in the wild, everywhere, for all humans. Yeah, so that's what I was talking about. And then the other one was, like simple, like using a better backbone. Mass CNN is really heavy. And there are many such works. So yeah, I don't think there's too much novelty in that autonomous driving paper that I mentioned, but that was just to make a point that, like people are working on such things, and that's what we did as well. No, no, you reduce the number of multiply and accumulate operations in the model forward prop by just keeping the most relevant ones. So you start with lightweight bottleneck and then, sorry, a backbone, and then you see, like how and what works. Yeah. Yeah, that's a very good question. So for in the sky, you don't really need to do forecasting. You don't really need to know where others will be, because it's kind of a static world situation. So usually you talk to your, your ATC, your air traffic control, and they'll tell you, okay, don't use this at all because it's taken up by some other flight during this kind of a time. So it's in some sense easier, but then there are challenges in the air. If you're doing just, there are no features. So people doing image processing will understand that it's all very plain and very like sky background, clouds. There are no image features. So you cannot really do a lot of, say, image-based things up there unless you look down. But then down, it's a weak perspective kind of a thing because it's so far away that you don't get the depth. Uh, uh, there. So, but yeah, autonomy is simpler for, say, drones. And this is why when you see that comparison, you will see that they're asking a lot more from drones to call it like level 5.
How do you ensure that the human driver is alert and paying attention when they are still required to be in the loop? For example, at
Yeah.
level 4 autonomy.
No, level 3 autonomy. Level 4, the car can go wherever. It doesn't have a steering wheel, but that's a very, very, very important question in my opinion. And it's called the alarm paradox. I mean, if you kind of, so because you're not supposed to be alert, so it's a problem. I mean, it's clearly a problem, and I feel that it shouldn't. Level 3, yeah, level 3 is tricky. So we're at level 3, and Waymo and Cruise are level 4 when they can drive without a driver. So that's level 4.
The next question by today, how do these autonomous vehicles decide which lane to stay on in a multi-lane highway? Is there some heuristic for that, or is that also learned by the system?
Yeah, so usually these are hand-coded systems. There may be some amount of, say, verification using a simulator and different use cases, but it's kind of a search algorithm based on the end cost that you want to minimize. So it's an optimization problem that you solve.
So the next question is by Akshay, which is an extension of what Shipit asked in terms of the ethical decisions related to autonomous driving. How is it made, and as in there is an incident to be responsible, that was something Shipit asked. There is a second part of the question. How does a car decide if it should nab its people in the car or others outside the car if there is an inevitable incident predicted?
Yeah, absolutely. Or there are two roads, and one you have your grandmother, and the other you have, young kids. So, yeah, I mean, I think we're far from those kind of ethical issues for now. I mean, we'll get there once we are truly at level 4 and we solve the long tail, and then we will, yeah, have these ethics in more limelight. But currently, nobody is truly focusing on them because there are other like major problems to solve.
The next question is from Mark. How much impact would a global connected system of autonomous cars have where every single car communicates with each other and shares data about the surroundings?
Yeah, I think it'll be really, really useful, and it'll make things, yeah, I mean, you'll have to worry about the bandwidth and the communication side of things, but assuming you have solved it, then yeah, I think be, it'll be easier to solve autonomous driving if you could do that. But there are a lot of, people don't want to talk to others, and there's a lot of, yeah, compliance problems and so on. So yeah, so campuses, warehouses are usually level 4, right? Because there is no driver and it just keeps doing its thing. It goes, fetches it, it makes sure it doesn't collide with other robots, it goes up, down, all that. So warehouses, robots, I mean, these are level 4s. But for campuses, there are trials happening. So Einride, one of the trucking companies, are doing those trials. Bosch is doing some, and so on. Yeah. Yeah, that's a good question. So some of it can of course be shared. For example, a car is almost a car, a person is still a person. So those basic models can maybe reuse, but yeah, the data set is different. And when you then go to higher levels in this stack, when you go to forecasting, path planning, control, so that is where you need to do maybe a market, something which is more tuned to the market. And countries like China, I mean, they have done a lot, and there's like Didi and AutoX and so on. But India, we're just starting. So there are some startups, -0 raised $2 million funding. There are other such startups, and then institutes like IIIT Hyderabad, which in collaboration with Intel are creating a data set, trying to handle these rural use cases. But yeah, we're still far from getting a real product. Yeah, I completely agree with you. And that's why my money is on the hybrid models, because they're sitting somewhere in the middle. And yeah, like there are, I think it'll eventually converge to something like that. Yeah, so the eventuality that you want, I mean, usually it's programmed for is at least come to a standstill, at least come to a halt, at least don't hit anything. But yeah, I mean, there will always be error. I mean, yeah, humans make errors as well. So there will be some amount of, but as long as you are maybe at, human level or better, I think you can have widespread use of these. That's what we're currently doing, but that's not enough. And not all such, like if you do that on a highway in America, that's not safe. And it's basically what it is designed to do, right? So all these cases are built in, and some people decide one over the other. Yeah, but human is the most important object that you can have. No, that's the end case, like, right? If you cannot do anything else, and you know that if you change the lane, you will hit somebody. If you keep going, you will hit somebody. Like, that's the worst case scenario. You try to then have the, like, pick a case with the least. Yeah, absolutely. Yeah, yeah. I mean, a deer, I mean, you're advised to drive over a deer on a highway instead of trying to brake. It's usually a deterministic engine. So these are the priors that I'm talking about, the rules that you can put inside the model to make sure that it's more, it's behaving more like you want it to for these corner cases.
We are running out of time, and there is already a question here. So, this question is from Shruti. Is some tuning applied in the direction? Let's say on the road, the object can move forward and backwards, rarely up and down, but in the air, it's possible to non-linear.
Yeah, correct. But air, we don't really worry about it too much. Like I said, in the air, it's kind of a static world situation that you care about, and all you want to do is mostly collision avoidance. But yeah, and cars also, you wouldn't really predict that they will come back. If they do, I think the autonomous agent will not be able to deal with it. I'm around. I mean, maybe, yeah, please go on. Very good question. So yeah. Correct, correct. But then you'll have to change the world and you'll have to put QR codes instead of traffic signs. No, that's not how QR codes work. I'm not sure. I mean, I didn't understand your question well. Sorry? हाँ बोलिए please. हाँ नहीं, लेकिन आपको QR कोड लगाना पड़ेगा बाहर जाके ना, और या अगर आप वैसे नहीं प्रोसेस होती है मैच, दैट्स नॉट हाउ इट वर्क्स. सो या विल टॉक ऑफलाइन एंड टेक दिस अप.
Thank you so much, folks. That's the end of the section. May I request Sundar to present the intro to Dr. Arjun.
Thank you so much. Appreciate. Yeah.
That was an enlightening talk, Dr. Arjun. So with that, we